In the last lecture, we looked at various factors affecting glass transition temperature of a product. Now let's look at the assumptions and limitations associated with the concept of molecular mobility. The first assumption that is made is that food contains numerous amorphous molecules, meaning the biomolecules present within food system like proteins and polysaccharides, they tend to act as amorphous molecules, which implies they exist either in their metastable equilibrium state or non-equilibrium conditions. The second important assumption is that kinetic techniques are much better in helping us understand, predict, and control several food attributes when we are talking about molecular mobility theory. Why? Because majority of foods, they tend to exist in either their metastable equilibrium state or non-equilibrium state. So an effective method to study molecular mobility is given by something called as WLF equation. So this will give you an idea about the speed of diffusion limited processes. WLF stands for William Landau Ferry equation. Now, if you look at this formula here, if you want to estimate molecular mobility at glass transition temperature, it is fine. You have Tg value here. But if you want to determine the molecular mobility at temperatures above glass transition, then what should this Tg value be substituted with is a question. So for that, the scientists, they have come up with saying that you can use or you can substitute Tg value with T-m value. This T-m value is also called as mobility temperature. So mobility temperature is a temperature at which when you supply enough heat, it removes all unwanted obstacles that have been causing decreased solute mobility. In other words, at this temperature, your solute becomes more mobile, it becomes more flexible, meaning it can easily diffuse. So these are the two assumptions that are important to molecular mobility theory. Moving on, let's now understand the limitations of this theory. First and foremost, microbiological stability cannot be explained using molecular mobility. What theory of water activity explains it better, as food is considered to be microbiologically stable if water activity is well below 0.6. The second one is chemical stability. So when chemical stability is supported by physical structure, then you can explain it using molecular mobility. But there are a few chemical reactions which are not supported by physical structure, like enzymatic reactions, impact of a specific chemical. They are not diffusion controlled, so they cannot be explained using molecular mobility theory. Finally, you have physical stability, storage like uptake of water by powders, collapse of powders during storage cannot be explained using theory of glass transition. Now, you have two more additional limitations to this theory, essentially associated with the assumption. So, the first assumption that we made was food contains numerous amorphous molecules. But in reality, when we talk about chemical reactions occurring within a food system, they are often centered around small molecules, including flavor components, alcohols, water, and whatnot. So the assumption that amorphous molecules are really involved in diffusion based or diffusion limited processes is a question. The last of assumption that we had made is there is an unfrozen part of water in your frozen food system. So the osmolality of this unfrozen part of water determines or is determined by presence of ice. So if you change the concentration of solute, the amount of ice formed can change. Meaning the system will try all its all the methods to get back to the same osmolality. This implies that the molecular mobility is not just dependent on the concentration of solute, but also the ratio in which reactants and products are mixed. In other words, the stoichiometry of the reaction. Thank you for staying with me through the video. In case you have any queries, please feel free to put them in the comment section and I'll get back at the earliest.